Okay, I'd like to tell you about the physical pendulum. Let me show you an example of a physical pendulum first. This is a scraper for scraping paint, and you see it's got a little hole there. And if I put a nail through that hole and just pull back, see how it goes back and forth? It has a period that it will oscillate at. Okay, this is not a simple pendulum. A simple pendulum has all its mass at one point, a distance, say L, away from an axis. This one is a physical pendulum because even though the axis is right here, the mass is spread out over this whole thing, and so you can't treat it as a point mass anymore. So let me show you how to derive the period of a physical pendulum. To do that, we need to start out with a couple things here. Let's start out with, you remember how, well, now you probably do, some of you that had this on a quiz, that A is equal to negative, for simple harmonic motion, it's equal to negative omega squared x. Another way to write that is it's the second derivative of x, which is acceleration, with respect to time, is equal to negative omega squared x. Okay, well, for this, we don't have so much restoring force as a restoring torque that's trying to rotate it back to its original position. So it wants to be in this position. When you displace it, the force of gravity is going to bring it back to its equilibrium position. So this is true for linear motion, but for twisting motion like that, we can say alpha is equal to negative omega squared times theta. Okay, so we're going to need that, and we're also going to need one other thing. We're going to need, I need to show you that when you're in radians, if you have the sine of theta, I want to show you that the sine of theta is very close. It's approximately theta for very small angles, for very small angles measured in radians. Okay, now to do that, I'm going to use the expansion for sine of theta. Sine of theta, there's an expansion series that equals the sine, let's call it sine of x. The sine of x can be represented with this expansion, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. And you see how this goes. Oops, this next one will be minus x to the 11th over 11 factorial, and it keeps doing that. Now, I want you to see something. If x is really tiny, if x is, like 0.1 or something, then when you cube it, it gets tinier, doesn't it? And then not only are you cubing it, but you are you're going to divide it by 3 factorial. And so each one of these terms becomes less and less significant. And so if sine of x really does equal all this stuff, well, when x gets to be really big, or excuse me, really small, these terms get incredibly small. And so sine of x is approximately equal to x, just this first term, because these other terms become insignificant when x is very tiny, like 0.1. In other words, go ahead and take the sine of 0.1. Put your calculator in radians. Take the sine of 0.1. And what you'll find is the sine of 0.1 is equal to is going to be equal to 0.0 0.0998. And so 0.0998 is almost equal to 0.1. In fact, the difference between these two looks like it's about 0.2%. So the difference between this and this, there's a 0.2% difference. Not 2% difference, but a 0.2% difference. All right, well, that took a long time to tell you that the sine of theta is, when you're in radians, it's approximately equal to theta for small radians. Okay, so let's get going on this derivation then. All right, so let's have a physical pendulum like this, maybe a board or something. Let's have the axis for this board be right here. That's the axis. And let's have the restoring force is acting from the center of mass, and it's acting straight down. And it's putting a torque on the board. And the torque that it's putting, if you pull this back an angle theta, a very tiny angle, we want this angle theta to be very tiny. This only works for tiny theta. When you pull it back a very tiny amount, do you see how this force, only a portion of it is putting a torque on this? In fact, what we could do is use the line of force to get the torque. So see this line of force? It's going to be, the effective lever arm is just this distance right here. That's the only part that's actually putting a torque on it. So the torque is going to be mg. This is mg. It's going to be mg times, if that's theta, then this is theta as well. And if that's theta, then if we call this distance d, the distance between the axis and the center of mass, if we call that distance d, then this is going to be, this distance is going to be d times the sine of theta. So that's the torque, mg d sine of theta. That's the effective lever arm. Okay, so alpha is the net torque over I. So alpha is the net torque, which is mg d sine of theta, all over I. I'm going to put a negative in here because it's, well, hang on for that negative. Hang on for that. Okay, so I'm going to, at this point, if I make theta really small, I'm going to say that goes to just mg d theta. Approximately, that's what alpha is. If theta is really small, say approximately, it's this. All right. Well, now I'm going to put a negative in here because I'm going to call anytime you pull it this way, that's a negative theta. You're actually displacing it in the negative territory, and so it's being restored in the positive direction. And so the negative on the theta in this would give you a positive alpha. I need to put that negative in there so that it can show that when this is negative and that's negative, it will actually pull it in the positive direction. All right, well, do you see that what I have here then is that alpha is equal to a negative mg d over I times theta. All right, so it turns out that this is omega squared. And if that's the case, then this square rooted is omega. And omega is equal to 2 pi over the period. So the period, come on over here with me, the period of a physical pendulum. If I bring this over here and that underneath, it's going to be 2 pi times the square root of I over mgd. That's the derivation.